So apologize, we're having a few technical difficulties. The microphone's not working at the moment, so we're going to go ahead and proceed. My name is Don Bailey. I'm chair of the Fellows Program here at RTI. It's part of a continuing seminar series that we have, bringing in great speakers from around the country and around the world. I'm going to turn it over to Dave Dayton, who's going to be introducing our speaker today. Just so let you know that on the table and online, you can download evaluation forms for the session. We'd really appreciate your feedback on it. Thanks very much for coming.
Thank you, Don. So we're very fortunate to have Dr. Gary Amy visiting RTI today, discussing some of his views on the WaterEnergy Nexus. It's a topic that's central to our water program in the Energy Technology Division and of interest across the Institute. Dr. Amy's main areas of expertise are drinking water treatment, wastewater reclamation and reuse, and specific expertise in membrane rejection, fouling, selective absorption, natural organic matter characterization, disinfection, byproduct formation, and control in natural systems. He currently holds 3 academic appointments. Apparently 2 wasn't enough, so he's got a 3rd one. So he's the Dean's Distinguished Professor in the College of Engineering and Science at Clemson University. He's also a visiting professor in the Chemical and Biomolecular Engineering Department at the National University of Singapore, and an emeritus professor and former director in the Water Desalination and Reuse Center at the King Abdullah University of Science and Technology, also known as KAUST, in Saudi Arabia. So at Clemson, he's coordinating a water energy consortium that officially launched about 2 years ago, July 1st, 2014. And it's a multidisciplinary group of over 40 Clemson faculty members who have assembled their knowledge and expertise to address the important global challenge of the water energy nexus. At the National University of Singapore, the Membrane Science and Technology Consortium was launched as a multidisciplinary group of almost 30 NUS faculty members and over 100 researchers with knowledge and expertise to address generational changes in water and energy security, climate change, and urbanization through advances of membrane science and technology. And at NUS, Dr. Amy serves as a senior advisor to a Separations Technologies Innovation Center focusing on membranes. And at KAUST, his major research emphasis was on low-energy seawater desalination technologies, energy harvesting, wastewater treatment processes, and managed aquifer recharge for wastewater reuse. In his 35-year career, he's published over 400 refereed journals, articles, supervised more than 50 PhD students, and he's a member of the International Water Association, the International Desalination Association, and the American Waterworks Association. He serves on the editorial boards of Water Supply and Technology, the International Ozone Association, the Journal of Drinking Water and Engineering. So please join me in welcoming Dr. Gary Amy as he presents his views on the water energy nexus and its extension into other critical resources.
Yeah, thank you, Dave. So today I have to speak like a professor without a microphone since the room microphone's not working. And also I put together a presentation with lots of animation to keep you awake, but apparently we can't do animation when we have a streaming version of this. So this is just the boring PDF version. So the water energy nexus, I'd like to talk about it, but I'd also like to extend the discussion into other critical resources. So let's first of all establish a vocabulary. What is a nexus? It's a relation or series of relations that will link 2 or more things. So we can think about the nexus at the interface of resources. We'll spend most of our time today on the water energy nexus, but we'll delve into the water food, the energy food, the water energy food nexus, and since food is connected to land, we'll talk a little bit about the land extension. And then given that waste is a resource, we'll talk about the water energy waste nexus as well. So it's really about a nexus of what we consider critical resources. So let's talk a little bit about the drivers here. We're faced with resource scarcity and security issues. And what are the drivers? Of course, climate change, population growth, urbanization, non-sustainable practices in how we use resources, and our reliance on non-renewable resources. So let's look at population and economic growth. So here we see a graph of population growth over time and global GDP over time as well. But of course, we see mimicking that trend. Oops. Uh-oh. Uh-oh. That's part of my... Okay, right. Okay. I missed something there, so... Okay, right. The animation was supposed to take care of that, so... Okay.
That one?
Yeah, but it's supposed to be another version of this, so... Okay, I guess the animation's not going to come out on this, so... Okay, bear with me. Okay. So now we're going backwards. Okay.
So now if we do that.
All right.
There we go.
All right. Okay, sorry for these technical difficulties, but so let's go in and talk in more detail about the water-energy nexus. And so when we think about the water-energy nexus, we're talking about the interconnectivity of water and energy. So obviously there's embedded energy in water, there's embedded water in energy, and we can think about the energy footprint of water processes and systems, the kilowatt hours per cubic meter of water. We can also talk about the water footprint of energy processes and power processes and systems. Here we're talking about the investment of a cubic meter of water to produce a kilowatt hour of power. And of course, associated with this are greenhouse gas emissions in terms of CO2 equivalents per cubic meter or per kilowatt hour. So the water energy nexus, this diagram from DOE shows the water flows and energy flows associated with an urban system. But what's interesting is to look at those points where there are potential intersections of water and energy flows. And this really represents the examples of the water energy nexus. Let's talk about water and energy trade-offs. So we can talk about water demand for power. This could be hydroelectric power. It could be cooling water for power plants. We can talk about water demand for fuels. This could be feedstocks for biofuels. This could be the water invested for extracting oil and gas, either conventional or unconventional oil and gas. Mining of energy sources like coal, and refining and upgrading fuels. And then the energy demand for water. Here we got to talk about the energy required for extracting water, for treating water, and for transporting and moving water. Let's talk about energy and water trade-offs related to quality. Obviously, energy affects water quality. We invest energy to treat water, to produce drinking water, for example, but also energy can pollute water when we think about thermal pollution from power plants. And water also affects energy quality. And one example of this would be enhanced recovery of oil and gas through water flooding, for example. So, water and energy solutions. What can we do to really reconcile some of these challenges posed by the water-energy connections? We can think about source switching for water or fuel. We can think about using impaired quality water, such as wastewater or seawater or saline waters for cooling water or for oil and gas extraction. We can think about fuels that require less water. We can think about more efficient and enhanced technologies that are either energy lean or water lean. Here we can think about water lean energy technologies, dry cooling, for example, waterless fracking, for example. We can think about energy lean water technologies, low energy membrane processes. We can think about using waste heat for water treatment. And we can also think about how we might look at distributed or decentralized water and energy technologies as well, and the use of smart technologies and grids. We can think about how we can apply improved data mining, informatics, and resource modeling, and also how we can move technologies forward through innovations in social science, policy, and market opportunities. So energy solutions by water sector. So we think about wastewater treatment. We can recover energy from wastewater treatment. Biogas can be recovered, methane. We can also think about applying renewable energy to drive water purification, such as desalination. This could be solar, this could be wind, but the problem with solar and wind is they have an intermittent character. But we can think about other innovations in terms of combining different energy sources. A combined cycle with solar and geothermal, where we use solar during the day and geothermal during the night. Water solutions by energy sector. So when we think about cooling, we can think about dry or hybrid cooling. Think about non-traditional or impaired quality sources of water for cooling, seawater or reclaimed wastewater. These present some operational challenges, however, in terms of managing scaling and biofouling. And in the oil and gas industry, we have to think about the oil and gas industry is also a water producer. Saudi Aramco, the largest oil company in the world, considers itself an oil company and a water company in terms of how they manage their water. So there's tremendous amounts of produced water in oil and gas extraction and fracking. We have to think about how we can treat and reuse this produced water, and even possibly imagine agricultural use of produced water. The constraint in terms of using produced water is that it's often saline. Okay, let's look at USA water withdrawals by category. And so if we look at these different categories, it's obvious that thermoelectric power and irrigation are the major uses of water in the US. But we also have to distinguish between withdrawals of water and consumptive uses of water as well. And so in thermoelectric power, we have a large consumptive use due to evaporative losses. So energy intensity of municipal water use. So if we look at the water cycle, in blue we see our drinking water part of the water cycle. In red we see the wastewater part of the water cycle. And then in green we see our interventions in capturing reclaimed water for reuse and recycling. I'm worried that this is part of the animation problem here. Yeah. So part of my animation has disappeared as this was created, converted to PDF. So, yeah. So I'm sorry, but okay. So let's take a look at the urban water cycle and the energy nexus. So if we look at how we move water, for example, in the drinking water side of things in the upper right, we transport water to the waterworks. We think about treating that water and then distributing the water. And we have to invest so many kilowatt hours per cubic meter to do this. And then once we go through the cycle of domestic water use, then we have to treat the sewage, collect the sewage, and dispose of the sewage. And so energy considerations are a dominant factor in the urban water cycle. Let's take a look at seawater reverse osmosis and think about the energy consumption issues related to seawater reverse osmosis for desalination. So seawater reverse osmosis system consists of an intake, pre-treatment, the reverse osmosis membrane step itself, and post-treatment. And so what we see here are a series of arrows that represent energy consumption. And the thickness of these arrows is really commensurate with the amount of energy that's consumed at the various stages. And so the real energy hog, so to speak, here is the reverse osmosis step itself. And so we need to think about how we can develop new disruptive technologies that will provide lower energy consumption in removing salts from water. Let's take a look at California. California is kind of interesting because California expends a lot of energy in moving water. What we have is dry and thirsty Los Angeles in the lower part of the state. And Los Angeles gets its water, Southern California gets its water from Northern California through the California Aqueduct and from Arizona, Nevada through the Colorado River Aqueduct. And what we see in the upper right-hand corner is a graph showing the energy expenditures just to move water from Northern California and the Colorado River to Southern California. Not treating it, just moving it over topographical barriers and so forth. And so obviously there's a lot of interest now in California in turning to the ocean. We can see that Los Angeles is right on the proximity of the Pacific Ocean and reinvesting that energy into desalination. So let's take a look at energy uses for different wastewater treatment processes. So here we see energy use, kilowatt hours per cubic meter. Some of these are fairly low energy intensity, trickling filters, for example. And then as we go to more and more advanced wastewater treatment, municipal wastewater treatment, we spend more and more energy. Now, one of the things that's really an energy sink is in wastewater treatment, we use biological treatment that requires oxygen, and so we have to aerate. And aeration is very energy intensive. The activated sludge system requires a lot of aeration. Membrane bioreactors require aeration not only for oxygen, but also for membrane fouling control as well. So these are very significant inputs of energy. However, all those organic constituents of municipal wastewater have embedded energy, these organic constituents. So can we imagine harvesting that energy? And can we imagine to actually see in the future the possibility of energy neutral or even energy positive wastewater treatment? So, environmental biotechnologies for sustainable wastewater treatment. So here we have an activated sludge system. We're investing so many kilowatt hours per cubic meter, most of that for aeration. And so what can we get out of this system? Well, we want to get water out of it, obviously, for potential reuse. Can we harvest energy as well? And also there are valuable nutrients such as phosphorus that are contained in the wastewater itself. And can we extract valuable materials such as phosphorus? So let's take a look at an anaerobic membrane bioreactor. So this is coupling the whole concept of a membrane bioreactor with anaerobic digestion. Anaerobic digestion of organic matter creates biogas, okay? Methane. So what we see here in the lower right-hand corner is a conventional activated sludge system. And if you saw my animation, what we'd be doing is replacing that conventional activated sludge system with a single tank. A single tank with the wastewater and an immersed membrane, a submerged membrane. And so what we do is we anaerobically treat that, we get out biogas. And so what advantages do we derive here? An anaerobic membrane bioreactor has a smaller footprint. Because of the membrane, it provides better permeate quality. And it also produces less sludge because of the anaerobic digestion, and it produces biogas. So here we have an opportunity to recover energy through the biogas. And so we can recover up to about a kilowatt hour per cubic meter of energy if we operate this system at 35 degrees centigrade, which is an optimal temperature. Now, if you're in Singapore or Saudi Arabia, where you have high ambient temperatures, you can begin to approach this. If you're in a colder climate, you have to reinvest part of that energy to heat up the water, so to speak. Okay, now let's look at where we are now. We're sort of stuck on concepts that have existed for decades, and we use these large centralized water systems that are really suboptimal. And so as we go to the future, what can we do to reinvest in new concepts of infrastructure that move away from centralized systems? So we can think about distributed or decentralized water systems. And so here we have a system where we use satellite water systems that tap into different water resources and also potentially produce different water qualities. When you think about all the water qualities necessary in an urban environment, they vary. Drinking water has to be the highest quality, obviously. So we can think about how we might produce fit-for-purpose water. We can imagine going through a treatment plant and after one step, withdrawing water for low quality requirements and going through additional steps as we move our way all the way up to drinking water. So in the future, we'll see more distributed and decentralized systems replacing large centralized systems. Now we think about desalination and wastewater treatment. The energy issues also translate into greenhouse gas emission problems. So we think about desalination. We have to think about carbon dioxide from electricity use. Here, this is one of the reasons we want to lower energy consumption. We look at wastewater treatment, things become a little more complex in terms of greenhouse gases. We get carbon dioxide from aerobic treatment. We get nitrogen oxide from nitrification, denitrification. And we get methane from anaerobic treatment and biosolids digestion. Of course, methane is a problem that can be translated into an opportunity if we harvest the methane for energy requirements. When we look at these greenhouse gases, we have to recognize, of course, that they have differences in their global warming potential. And methane is much more problematical than carbon dioxide, for example. Let's look at water use for thermoelectric power generation and other sectors. So here we see about a 50 to 60 year period of record, billions of gallons per day of withdrawals. And what we see is gallons per kilowatt hour in the bars. We're becoming more efficient, but of course we're building more power plants as our population growth increases and our power requirement increases. And so we see the amount of water that we withdraw for thermoelectric power generation increasing, and most of that is fresh water. And so here the interest is moving away from fresh water and looking at seawater, brackish water, and even wastewater for cooling purposes. So let's look at thermoelectric power generation cooling options. We can think about once-through cooling. And this is how many of the cooling plants along the coast of California operate. However, there are discussions and regulations underway to limit the use of once-through cooling. And so we may see that we have to move more and more toward closed-loop evaporative cooling, where we actually have a cycle of concentration and a blowdown that we create that is high in salinity. And so this requires that we manage the salinity of the blowdown stream. We can move to dry-cooled power plants or even hybrids of dry and wet cooling. So here we see a little simple schematic of a dry cooling technology where we look at using air as opposed to water for cooling. There's still an energy investment here, right? So we still have to invest some energy to provide this cooling, but you're moving away from the water investment if water scarcity is the driving issue. So let's look at opportunities for power plant water use reduction. So what are some of the things we can do? Well, coming out of that cooling tower is a lot of water vapor, right? Saturated water vapor. So how can we think about condensing that water vapor? Using less water for cooling, more efficient cooling. Treating the blowdown water for reuse. Looking at utilizing waste heat and improving the cycle efficiency. So we can really attack this problem on several different levels in terms of water use reduction. Let's move from cooling to fracking. So we think about water use in shale gas generation through fracking. We start out with the fresh water source, and we add some fracking chemicals, and we end up with our fracking fluid. And so we develop our fracking well, and then we end up with our flowback water initially, and then more long-term we end up with our produced water. And so what do we do with this poor quality water that we've created? We have to think about opportunities for reusing or treating and releasing back into the environment. So we have to think about innovative technologies for produced water treatment and reuse. So fuels production, water cycle, water life cycle, and fracking. So we have water acquisition, chemical mixing, well injection, flowback and produced water treatment disposal. We want to interrupt this linear scheme to make it more of a circular scheme in terms of reuse and treatment of produced water. Okay, so produced water in some of these slides did not translate very well when I lost the animation. Sorry about this, but I had my animated version perfect this morning. Tested it out at 5:30 a.m., so I didn't know I was going to be stuck with a non-animated version, but in any event. So produced water in conventional oil recovery. So we go to Saudi Arabia, and for every barrel of oil that you produce up to 3 to 4 barrels of produced water. And so what can you do with this produced water? You can re-inject it into the oil reservoir. And this is known as the practice of water flooding that can be used to maintain pressure and enhance oil recovery from that oil reservoir. And we can also use it in the drilling and completion of wells. So let's look at produced water from an unconventional fossil fuel. So let's move from conventional to unconventional or fracking. So what does it take in terms of developing a hydraulic fracturing well? So we have about 50,000 to 150,000 barrels of water just to create the well. And then after a well starts operating, we get about 15 to 80% of the volume that's recovered as the initial flowback water that contains all of those drilling chemicals and drilling fluids. And then more on a long-term basis, we get 10 to 1,000 barrels per day of produced water from each production well. So obviously we have to be able to manage these tremendous volumes of water that are often in very remote locations. They're not next to a sewage treatment plant. They're often next to out in remote locations where you have to think about either on-site reuse or even the possibility of truck transport to an off-site facility. So fracking produced water quality. So we look at some example produced water quality from fracking operations in Texas and West Virginia. The first thing we can see is this is pretty salty stuff. It's often hypersaline and in many cases more salty than seawater. So this is a big constraint. We have to think about desalination if we want to reuse this water. There's also variability of produced water quality. So here we see different produced waters from an oil field, gas field, coal bed, methane field. And what we see are variations in salinity, very high TDS levels to lower levels in coal bed methane fields, big variation. We see a lot of organic matter as evidenced by the total organic carbon. And we see a lot of oil in the produced water, often in the form of emulsions, oil and water emulsions. Another thing to take note of is that in conventional oil fields, like Saudi Arabia, for example, when you bring up oil and produced water from a conventional oil field, that water has latent heat. It can be up to 70 degrees centigrade. And that is really a form of quote-unquote waste heat that could be used to potentially drive a desalination process. So produced water treatment and reuse. What are some of the options? On-site treatment versus transport to a central facility, which is what you want to avoid, of course. And you can think about all the greenhouse gas emissions as this caravan of trucks moves water to a central facility. There are conventional technologies that we can use, such as evaporation, but on the horizon are novel technologies. Membrane distillation only requires a slightly elevated temperature to move water vapor through a membrane. And remember that latent heat of produced water? That alone could drive membrane distillation for desalting purposes. Forward osmosis can be used to concentrate brines, concentrate waste streams. If you're going to transport water by trucks, if you can reduce the volume 3 to 4-fold, that has a tremendous advantage. And then also, what about all those oil and water emulsions? How do we really manage those? Those have a tremendous fouling potential for reverse osmosis if we wanted to use that. There's a lot of interest in using ceramic membranes for removing oil and water emulsions. Let's look at the freshwater intensity of energy production. So we're looking at here at barrels of water per barrel of oil equivalent. And down on the lower part of the graph, we see shale gas. We don't really have to invest that much water in shale gas compared to other energy production options. We look at electricity in a coal-fired plant. But at the top, what do we see? Ethanol, biofuels, and the tremendous water investment required for producing biofuels and biofuel feedstocks. Let's talk a little bit about biofuels, water requirements for biofuels. So obviously, when we think about energy opportunities and alternatives, bioenergy really represents potentially the biggest water consumer compared to other energies. And just sort of a rough rule of thumb, it takes an average of 2,500 liters of water to produce a liter of liquid biofuels. So that's quite an investment of water for energy. Now let's move this discussion now beyond the water-energy nexus, and let's connect it to other resources. And so other resources we can talk about briefly will be food, agriculture, and we can talk about both the water and the energy footprints of food production, talk a little bit about crops as biofuels. We'll talk about land intensity of food production, land degradation, and then we'll end up with waste and look at embedded energy and waste and recovery of valuable materials. So the water-food nexus. So water-food nexus, we're talking about water required for agriculture, food production. Agriculture represents globally the highest water use sector in terms of water withdrawals and use. This, of course, involves management of land resources and the water footprint of food production. So this all leads to the very interesting concept of virtual water. So if you had a sandwich today and there was beef in it, I don't know if there was, how much water did it take to create that beef? How much water does it create to create a hamburger and to grow a cow? So we really have to think about cubic meters of water to really produce a kilogram of beef. And we have to think about the differences between different food sources. There are many opportunities, given the freshwater scarcity, to think about how we could go into the concepts of saline agriculture and think about how we can genetically modify crops to be more salt tolerant or even drought tolerant. And we can think about, given land considerations, how can we grow food without soil through concepts of hydroponics, for example. And then finally, how can we extract nutrients for fertilizers? So, the water-food nexus. We have to think about a virtual water footprint. So, all crops and foods have a virtual water footprint. A raw crop has a footprint, and a processed crop has a footprint as well. So, if you're talking about wheat, or if you're talking about bread, there's a certain water footprint. Now, we think about global commerce and the movement and export and import of food. What we're actually doing is moving and importing and exporting water in the form of virtual water. So this little diagram just tries to show you the differences in terms of the virtual water footprint of different foods and different processed products from food products as well. And of course you can see beef is a very big water consumer compared to wheat and barley, for example. So mitigating measures, what can we do? We can think about improved irrigation efficiency. And we can also think about moving away from fresh water and irrigating with non-traditional waters. Of course, we have a long history of using reclaimed wastewater for crop irrigation. The big issue there is public health risk in terms of pathogens. But the real opportunity is with saline water, and to use saline water for salt-tolerant crops or to genetically modify crops to make them more salt-tolerant. And so here we open up the doors to the opportunity for saline agriculture. Now, when we think about managing water for irrigation, we have to think about how we optimize things. And so there's a whole field of precision agriculture that is really the basis for how we operate so-called smart farms, real-time monitoring of water conditions, soil conditions, and nutrient conditions for operating a smart farm. Now let's look at saline water resources in California. We know there's a drought in California, and they're thinking about desalination. But besides the ocean, there are inland sources of saline waters as well. Agricultural drainage water, brackish groundwater. Even the Colorado River water has moderate levels of salinity, and wastewater has moderate levels of salinity as well. So here in California, there are opportunities to implement saline agriculture if we can make crops more salt tolerant and manage soil salinity. Now, some interesting developments in Australia. So drip irrigation has been around for a long time as a way to improve the amount of water that is applied to a crop. But what if we have saline water? Could we take a drip irrigation tube and replace it by a membrane-like tube, a reverse osmosis-like tube that would not only distribute the water, but desalt the water as well? So this is the concept of membrane-facilitated subsurface drip irrigation. And this would open some further doors to saline water agriculture. Now we think about growing crops on salty water. Here we see a graph showing relative yield for salinity level with different groups of crops, including halophytes, salt-tolerant crops. Now, even in salt-sensitive crops, we see there's still ability to grow crops in saline water, but there's trade-offs. Trade-offs between the yield and the salinity. So we have to recognize that trade-off, and we also have to think about how we might increase the salinity tolerance of salt-sensitive crops. And there's a lot of work ongoing in areas such as tomato breeding and genetic modification. So water use intensity of some major biofuels. Here we're looking at liters of water per liter of biofuel. Tremendous variation depending upon the feedstock, sugar beets versus soybeans. But this is only part of the picture. We're trying to grow food for nutrition, right? So we also have to think about the nutritional value of the food itself. So besides just water per kilogram of food, we can also think about how much money we invest per cubic meter, but also the kilocalories of nutritional value that we get out per cubic meter of water that's invested. Now, I'll skip over this. Okay. Now, food and fuel are competing for not only water, but land as well. So this graph really shows the irrigation and land requirements to produce 1 liter of ethanol. And so if you look at sugar cane, what we see is that sugar cane, relatively speaking, is more water intensive than land intensive. Switchgrass is vice versa, more land intensive than water intensive, and sorghum is on the extreme in terms of being both water intensive and land intensive. So we have to think about not only the investment of the water resource, but the land resource as well. Okay, so what can we do in biofuels? So we have to think about as we go forward, we're moving from first generation biofuel feedstocks, i.e. crops intended for human consumption, like corn. And because of the conflict between food and biofuels, we're trying to move now to non-food biofuels and feedstocks. Now, the basic hope or the basic premise is that second generation feedstocks should grow on marginal land, they should require less water, and they should also be able to use poor quality water. Unfortunately, reality versus these goals has not borne itself out. So we're still an escaping goal to really achieve these ideal characteristics of second generation food crops or biofuel feedstocks. Another opportunity, going beyond just switchgrass or sorghum as far as potential feedstocks that are not food sources, we can think about algae and even the opportunity to grow saltwater algae for biofuels. This could be done inland in brackish water ponds or raceways or coastally in terms of algal cultivation pens. Energy food nexus. Okay, I'm going to skip over that. Okay, now, the energy food nexus, we're confronted with a key problem here. And if we think about growing corn, 8 bushels of corn creates 21 gallons of ethanol, but that's enough to feed a person for a whole year. And so you have this sort of conflict between water scarcity, energy scarcity, and food scarcity, and how you resolve that. And so this is one of the reasons about moving towards second generation biofuel feedstocks. Okay, water energy waste nexus. Let's bring waste into the picture here. So the water waste nexus, we recognize that waste streams such as brines do contain energy, and energy is embedded in waste. Energy is embedded in waste streams. And besides the energy that's embedded in these waste streams, there are also potentially valuable materials. There is lithium in seawater brines. Lithium is very important now, of course. And there's phosphorus in wastewaters as well. So this opens the door to the water, energy, waste nexus. So let's think about a wastewater treatment plant as more than just an ordinary sewage treatment plant. Let's think about it more boldly as a resource recovery plant. And this is sort of a paradigm shift as we think about imagining wastewater as a waste to really a resource. And this is really the business case for promoting this. So if we have a wastewater, what do we get out of it potentially? Water for reuse. We also can get energy, potentially in the form of biogas, we use that example, and also valuable materials, for example, phosphorus from wastewater. Okay. Now, finally, let's extend this discussion now to include land. So the water, energy, waste, land nexus. Now, the reason I'm doing this is I spend part of my time in Singapore. Singapore is an island nation with a very high population density. And land is critically important to Singapore, how they manage their land in a very high population density country. So they're looking for integrated solutions that really address the issue of water, energy, and land. Let's think about some of the things that they are doing there. So let's think about land use and land intensity. So one thing we can do is facility integration, co-location of facilities. We can co-locate wastewater treatment plants with anaerobic digestion facilities. And so what we can do is we can take the biosolids from the wastewater plant, and we can take food waste that have been captured from Singapore and anaerobically digest them for methane. We can co-locate desalination and wastewater reuse facilities. And this opens the door for the capture of energy from salinity through salinity gradient energy processes such as pressure retarded osmosis. And we can also co-locate industry facilities with desalination facilities, particularly if those industries have a lot of waste heat available for recovery and utilization for driving desalination. Another area of interest of Singapore, it is an island nation surrounded by the sea, and so they're looking at opportunities for seawater agriculture using halophytes and aquaculture and algal cultivation for biofuels. So extending that water energy nexus and looking at decentralized systems and distributed infrastructure in Singapore. So looking at the integration of existing centralized systems, the building of new decentralized systems and their integration. The interest in satellite membrane bioreactors, rather than just one large sewage treatment plant, to have satellite membrane bioreactors and decentralized wastewater management, and even taking decentralization to the viewpoint of a building. In a building in Singapore, you have a small village. And so what can you do in that building? You can think of on-site wastewater treatment and reuse, on-site solid waste management, on-site anaerobic digestion of food. There's a lot of interest in urban farming in Singapore. You can digest urban farming waste, on-site reclaimed wastewater use for urban farming, captured root runoff for urban farming, and on-site wastewater and solid waste segregation. So my last slide is sort of the vision for Singapore in terms of how they really envision addressing the water, energy, waste nexus. So in the lower left-hand corner, they're building seawater desalination plants, creating clean water from seawater. But they produce a lot of seawater brines. As they desalt water, they're left with brines. We'll come back to that in a moment. In the upper right-hand corner, they have used water. This is sort of the public relations term for sewage. We talk about sewage. That doesn't resonate very well with the public. They call it used water for public relations purposes. You have your water reclamation plant. You have a treated effluent. And then you go to their new water plant, where the goal is to produce potable water from sewage. Through the new water plant and the brine, you can create salinity gradient energy. Through the digestion of wastewater solids and food waste, you can anaerobically create biogas and create energy as well. So this is the approach to really optimize land use, reduce energy demand, and increase resource efficiency in Singapore. So I thank you for your attention.
I think Professor Amy has left us for a few minutes for questions. So if anybody has any questions, feel free to grab a mic.
Thank you. Very interesting presentation, and especially interested in the granular water use at different water qualities. What kinds of bottlenecks do you see in terms of the sensors, the measurement techniques or devices, as well as analytics that would permit that to happen faster?
So first of all, this whole concept of fit-for-purpose water, I think probably the most advanced facility in the world today is in California, the West Basin Municipal District. What they do is they take sewage, and they literally have a half a dozen processes, but they can withdraw water from various points. But you also have to have proximate users, and in the area of this municipal water utility, there's a lot of industry activity. So you have to think about planning in terms of how you can concentrate industrial activity. This is happening in Saudi Arabia in terms of industrial complexes, and in Singapore they dedicate a whole small island to it. But secondly, it's also about real-time information on water quality and water treatment conditions. We have a lot of sensors, of course, but to really translate that into instantaneous feedback loops and so forth. So we have to think about how we can go just beyond salinity, temperature, pH, and so forth, and more real-time specific component sensors. For example, we have membranes, we have sealing. Calcium, we need to be able to react to changes in calcium because of calcium precipitates on a membrane. So I think broadening the whole possibility of measurements, real time, not in the lab, real time, I think is very important. Okay, I have a different audience out there as well. Okay.
So you said two things which I found compelling. One was distributed water treatment, let's call it, and the other is the use of brackish water. In other words, either direct use, because it can be, or treated for use. So what would you suggest? First of all, in the oil and gas industry, which I came from, there was a lot of pushback for using brackish water because, for whatever reason, it ain't broke, so don't fix it. So what do you feel are the compelling propositions that would make it happen? Is it technical? Is it policy? What would it be?
It is obviously technical, but very important is policy. Saudi Aramco, as a company in Saudi Arabia, has a corporate policy that in the future, all their future water projects will not tap into fresh groundwater. So they're moving away from using groundwater in the oil and gas industry. So they have seawater, and they're thinking about, can we inject seawater to maintain pressure in the oil reservoirs? They can, but if they partially desalt that water, they can even enhance the oil recovery from those reservoirs as well. So the technology developments are critical, especially in terms of making them less energy intensive. But equally important is policy. And that's really about not only government policy, but associated regulations. And so every technology is a combination of the scientific advancements, but also the soft side as well. And don't forget the public. There's a lot of public opposition to desalination. Much of it, quite frankly, unjustified, but we aren't doing a good job of communicating to the public what a desalting plant does and why it could be a greener technology if we work at it.
No, but one of the pushbacks on desalination, especially inland, away from the ocean, is of course the residual brackish water from. I mean, a good 50% is. And so what you do with it, now, you spoke of some technology which I had not heard of before, this salinated gradient method. But something like that may be needed. The public right now correctly feels if you have desalination plant in the middle of the country, what are you going to do with the residue?
So you are correct in identifying the major constraint to inland desalination, and that's the brine management. And so the brine management is the volume of the brine and the salinity of the brine. And so the extreme is to think about zero liquid discharge technologies that will virtually remove all the water and leave a solid residue. Along the way, you might think of, are there valuable materials I might extract from that? Salt, sodium chloride for table salt doesn't have much of a value, but gypsum, maybe you could extract gypsum, for example. So obviously, zero liquid discharge technologies are an important opportunity to do more in inland desalting. And also, we can do other things with that brine. There's some work looking at using brackish water desalination brines to grow salt-tolerant crops. Can we use it for agricultural purposes, a beneficial use? So definitely brackish water desalination is the issue. Is the brine? That's not an issue in the seawater situation. You have the whole ocean out there to basically accommodate the salt that you originally took out of the ocean. You're simply putting it back in an environmentally safe way, of course.
It seems like the places where there's innovations is being driven by necessity, like in California and Singapore. Do you think there's a way to sort of something like a water credit tax system that would sort of drive that in other places? Does that have a place?
Yeah. Well, what's happening in California is just a foreboding of what's going to happen over the next 50 years or whatever in other parts of the world. And so water scarcity is going to become more widespread, not only because of climate change, but because of population growth as well. So we have to think about how we correctly value water. Go home and look at your water bill. What did you pay for your monthly water bill? $20 for 1,000 gallons or something. It's vastly undervalued. And we have to think about a correct value for water. And that's really a policy issue as well. So certainly regulations and policy are necessary. And the other thing, going back to the public, is we have to convince the public that we can make these technologies greener, lower greenhouse gas emissions and so forth. So if we can run desalination through solar power and avoid the greenhouse gas emissions, that's a big incentive for the public buy-in. So.
Well, this is going to be a question for everyone. How many of you have visited a wastewater treatment plant in the city?
Oh, okay.
So that's actually you. I don't know if it's representative of the population. That's actually a high amount. Maybe you had a business trip at RTI, but that's a good thing. You need to see, because I think it's been hidden from us, what it is really, and that in part is a problem, I think. But you guys are a good example.
But just a comment on that, Hervé, is Singapore is like the model for the world about how to bring in the public into water management. People in Singapore, from the time they're in school, are brought up to recognize the value in water and appreciate water as well. So we have to do that at the educational level, beginning from lower grades on up, and we really haven't done a good job of that yet. So if you really want to look at how a country should manage water, look at Singapore. It's not the U.S., it's a small island nation, I understand that, but just some of the sort of the social science and public incentives issues. So.
That will end, and thank Dr. Amy one more time.
Thank you.